For my design project, I chose to create a circuit for a flashlight powered by two AA batteries. This flashlight also has an option for bright or dim light using a single pole double throw switch, and also has a capacitor for a battery backup. At state 1, the flashlight is providing bright light, and this is the equivalent circuit to be analyzed. First, I found the equation for the voltage drop across the capacitor. V of t equals the open circuit voltage plus V naught less the open circuit voltage times e to the power of negative t per tau. In this circuit, the open circuit voltage is 3.6 volts and V naught is equal to 0 volts. And tau equals to the Thevenin resistance times the capacitance, or 1,140 ohms times 1 farad equals 1.14 seconds. Therefore, the expression for the voltage drop across the capacitor is equal to V of t equals 3.6 volts minus 3.6 volts times e to the negative t per 1.14 seconds. To solve for the currents, I used KCL and checked with KVL. Taking KVL at node A, current in equals current out, so I1 equals I2 plus I3. Using Ohm's law, I2 becomes VA minus VB over 140 ohms, and I3 becomes VA minus VB over 1 kiloohm. Plugging in known values for VA, we find that I1 equals 0.029 amps, I2 equals 0.0036 amps, and I3 equals 0.025 amps. In checking with the KVL loop, I took KVL around loop 1 to find that negative 3.6 volts plus V1, the voltage across the 140 ohm potentiometer, equals 0. Therefore, V1 equals 3.6 volts. Using Ohm's law, I3 times 140 ohms equals 3.6 volts. Thus, I3 equals 0.025 amps, which checks out with my KCL equations. Taking KVL at node 2, negative V2 plus 3.6 volts equals 0, and simply V2 equals 3 volts. And using Ohm's law, I2 times 1 kiloohm equals 3.6 volts, which simplifies to I2 equals 0.0036 amps. When the switch is at state 2, the flashlight is providing dim light, and the equivalent circuit for state 2 is pictured. The analysis is very similar. So first, I again found the equation for the voltage drop across the capacitor. Everything else is the same except for state 1, except for the Thevenin resistance, which is now 1,300 ohms. So therefore, tau becomes 1.3 seconds, and V of t equals 3.6 volts minus 3.6 volts times e to the negative t per 1.3 seconds. Again, KCL equations were used to solve for currents, and in a similar way, we found that I1 equals 0.0156 amps, I3 equals 0.012 amps, and I2 equals 0.0036 amps. Again, checking with KVL loops, KVL across loop 1 found that V1 equals 3.6 volts, and using Ohm's law, I3 times 300 ohms equals 3.6 volts, and I3 equals 0.012 amps. Using KVL loop 2, V2 equals 3.6 volts. Using Ohm's law, I2 times 1 kiloohm equals 3.6 volts, thus I2 equals 0.0036 amps. So what do all these numbers mean? In order to alter the brightness of the LEDs, I needed to adjust the current flowing through them, and therefore I was adjusting the resistivity. The maximum current through the LEDs I used was 30 milliamps. So therefore, for the bright light, I have 25 milliamps flowing through that LED, controlled by a 140 ohm potentiometer, and for the dim light, there's 12 milliamps of current through the LED, regulated by a 300 ohm resistor.